I've got a really special video for you guys today. So this is part of my series on Vertex Algebras, and in this video we have a guest. And the guest is Richard Borcherds from the University of California at Berkeley, and he's the winner of the 1998 Fields Medal. And he's going to talk about the genesis of Vertex Algebras. So the story goes that he introduced the notion of vertex algebras along the way of proving this thing called the Conway-Norton conjecture. Okay, so I'd like to extend my extreme gratitude to Professor Borcherds for contributing to this channel, and I think in the future I'm going to have more guests and interviews as part of our normal programming. Okay, enjoy the video.
This talk will be about the origins of the theory of vertex algebras. It's going to be a bit different from my usual talks because it was in fact commissioned by Michael Penn, who has a YouTube mathematics channel on which he has a few videos on vertex algebras, and he asked me to provide a video discussing the beginning of vertex algebra theory. So this is a sort of historical account. It's based on my memory of things that happened more than 35 years ago, so I've doubtless misremembered a few things. So first of all, let's give the original definition of a vertex algebra. Now, the original definition is really clumsy and a total mess. So it looks like the following. What we do is we have some sort of module V, and we have an infinite number of products on V, taking V times V to V, taking U and V to a product um of V, where m is an integer. And these products satisfy various identities. So V has a sort of identity element such that 1nw is naught for n not equal to -1, and 1 minus 1w equals w. So that's a sort of analog of the identity. And it also has a sort of derivation with divided powers, given by n of 1 is equal to d to the minus n minus 1 of u. And it satisfies some identities. And the first of these identities looks like this. It says u and v is sum of -1 to the n plus I plus 1 of d to the I v n plus I u, sum over all I. And the next identity says that m of v n w is equal to sum over I greater than or equal to 0 of mi times -1 to the I guess, of u m minus I v n plus I w minus -1 to the m of v m plus n minus I u I w. So this definition raises several questions. First of all, is there a better definition? Because this is obviously rather a mess. And the answer is yes. In fact, 2 or 3 years after this definition, Frenkel, Lepowski, and Merman reformulated the definition in terms of formal power series, which makes it look much cleaner. I'm not going to give the cleaner definition because that's the standard definition which you can find almost everywhere. This is the historical definition. You can rewrite all these operators in terms of formal power series. So what you do is you have a formal power series in some formal variable z, which is sum over n of un times z to the minus n minus 1. So you can rewrite everything as in terms of these formal power series, and that cleans it up. So I'm not going to talk much about the better definition. What I'm going to talk about is the obvious question: how did anyone think of this? So how did anyone find this weird definition? Well, the story starts, well, more or less with the Leech lattice. So the Leech lattice is a lattice in 24-dimensional real vector space. And it's really famous because the automorphism group is more or less a double cover of Conway's simple group, Conway's largest simple group. So Conway became very famous in the 60s for discovering a new sporadic group whose automorphism group was the Leech lattice. And Conway and his co-workers were doing a lot of calculations with the Leech lattice, and one of the things they did was they figured out its covering radius. And the covering radius is square root of 2. That means if you have a sphere radius square root of 2 around every lattice point, it just covers the lattice. So for a hexagonal lattice, the covering radius would be the smallest number such that balls around the points just cover the lattice. So the points furthest away from the lattice points are called the deep holes. And Richard Parker noticed that the deep holes of the Leech lattice seem to correspond in a rather mysterious way to Niemeyer lattices. So the Niemeyer lattices have been classified a few years before by Niemeyer, and they're the other even unimodular lattices in 24 dimensions. And he found 23 classes of these, well, 24 classes, including the Leech lattice. And Richard Parker noticed that 2 or 3 of these classes seem to correspond to certain of the deep holes. Anyway, Conway and Parker and Sloan got very excited about this and classified the deep holes and found there were 23 classes of deep holes. This was a huge, complicated calculation taking, 100 or 200 pages, real mess. Anyway, Conway used this result to give the following very striking result about reflection groups. So what he did was he calculated the reflection group of the lattice II1,25 or II25,1. There are 2 conventions for which round you put these. So this is an even lattice, and it's unimodular, which means the volume of a fundamental domain is 1, and it lives inside Lorentzian space R1,25. And you can look at its automorphism group, and its automorphism group has a big reflection group as a subgroup, and Conway calculated this reflection group. In fact, he found its simple roots. The simple roots of the reflection group turn out to be the same as the Leech lattice. And the simple roots of a reflection group are sometimes called the Coxeter diagram, or sometimes the Dinkin diagram, depending on whether you're a geometer or a Lie algebra theorist. So we have this weird result that the Coxeter diagram, or the Dinkin diagram of this lattice, is the Leech lattice. Well, what on earth does that mean? I mean, a Leech lattice isn't a Dinkin diagram. I mean, a Dinkin diagram is something that looks like this. Well, you can turn the Leech lattice into a Dinkin diagram as follows. What you do, the points of the lattice correspond to the points of the Dinkin diagram, and you need to draw lines between the points, and you draw lines between the points of this. So if you've got 2 lattice points, lambda and mu, such that lambda minus mu squared equals 4, so these are as close as possible, you draw no lines between them. You draw 1 line between them if lambda minus mu squared equals 6, and if lambda minus mu squared is greater than 6, you draw something more complicated between them. It's not really a double line because a double line means something else, but anyway, you can turn the geometry of the Leech lattice into a Dinkin diagram. And I was a research student at the time, and Conway gave me some more geometric calculations to do with the Leech lattice to keep me out of his hair for a bit, and in particular he asked me to classify the other holes, so I went off and did that. And in order to do this, it's quite useful to use Conway's observation that the Leech lattice is really a Dinkin diagram. And meanwhile, Katz and Moody had invented Katz-Moody algebras. So the usual finite dimensional Lie algebras, such as E8, have certain Dinkin diagrams. And from this Dinkin diagram, you can write down the Sayre relations, and that gives you a finite dimensional Lie algebra. And Katz and Moody noticed that you could take more or less any graph you like. For instance, you could take this one, 1, 2, 3, 4, 5, 6, 7, 8, 9. So if you write down the Serre relations for this, this doesn't give you a finite dimensional Lie algebra, but it gives you a Kac-Moody algebra. The name came later. So this is actually the Dinkin diagram of the so-called affine E8 Lie algebra, which is more or less E8 over a ring of Laurent polynomials, give or take a central extension. And so I've been fiddling around with the Leech lattice, thinking of it as a Dinkin diagram, and I got this idea, you could form a Kac-Moody algebra by taking the Leech lattice as the Dinkin diagram. So I went and told John Conway about this, and he sort of very kindly told me that, yes, they already knew about this, and he and Queen and Sloan actually had a paper pointing this out. So this is the normal result of any idea you have in mathematics. It turns out to be either wrong or trivial or known already, and this one was known already. Anyway, actually John Conway very kindly added my name to this paper they had already written, so I got my name on a paper that I had absolutely nothing to do with. Anyway, I got rather intrigued by this Lie algebra and started doing some calculations with it to see what was going on. And one thing you can calculate is you can calculate its root multiplicities. So the roots of the Lie algebra are elements of this lattice, this 26-dimensional Lorentzian lattice. And the root multiplicity is just the dimension of the corresponding root space. And you can calculate the dimension of various roots. So if we have a root R, then the dimension of the root space is given as follows. First of all, if R has norm 2, then the dimension is 1, and these are just the so-called real roots, so that's kind of trivial. If the roots have norm 0, then it's easy to calculate the multiplicity of the roots. The multiplicity is either 24 or 0. So what happens is this has 24 times infinity orbits of norm 0 roots corresponding to the Nemi lattices. The correspondence is if you've got a norm 0 vector, then its orthogonal complement modulo omega is a Nemi lattice. So there are 24 orbits of primitive norm 0 vectors. And for the ones corresponding to the Leech lattice, the multiplicity is 0, and for the other Nemi lattices, can't spell Niemeyer. It's got too many I's and E's in it. So the Nemi lattice, the 23 Nemi lattices give you 23 times infinity orbits of norm 0 vectors with multiplicity 24. So that was easy. Next, you can look at roots such that R omega RW equals -1 for a norm 0 root. And these also turn out to be reasonably easy to calculate using the theory of affine Kac-Moody algebras. And the result is as follows. Suppose you take the Ramanujan's tau function, which is product q times product of 1 minus q to the n to the 24. So this is a very famous function whose coefficients are Ramanujan's tau function, which is a different tau from this one, but never mind. And you take 1 over delta of tau. So this turns out to be q to the -1 plus 24 plus 324q plus 3200q squared. And the multiplicities of roots that have norm -1 with a norm 0 vector turn out to be these coefficients here. So this is if r equals 0, this is if r equals -2, and this is if r equals -4. So that's only if it is in a product -1 with a norm 0 vector. And I tried calculating the multiplicity for other roots r. So if r is -2, it turns out there are 121 orbits of such roots, and 119 of them have multiplicity equal to this number 324, and 2 don't. 2 have multiplicity less than 324. So I got rather excited about this and went around telling people. And as I mentioned before, any result you find turns out to be either trivial or wrong or found by somebody else. And it turns out these results had already been found by Igor Frankl. In fact, he'd gone further. So first of all, Frankl had noticed this result here, that the multiplicities with respect to a norm, with respect to these sorts of roots, have multiplicity exactly these numbers. But he had also gone further, and he had shown that for any root R, the multiplicity is less than or equal to P24 of 1 minus R squared over 2, where P24 are these coefficients here. So he showed that these numbers here were an upper bound not just for norm minus 2 vectors, as I'd found by this huge calculation, but he managed to prove this was an upper bound for all vectors. So yeah, that was a bit disappointing to discover that my nice new result was already known. But so I went off and tried to study Igor's result, and his result used the no-ghost theorem from string theory. And it's a theorem about involving vertex operators, and we're finally getting to something related to vertex algebras. There's a lot of nonsense written about string theory on YouTube and the internet, mostly by people who don't seem to actually know what string theory is. String theory, whether or not it turns out in the end to be useful in physics, is a very interesting and rich mathematical theory. The part of string theory used for Frankl's result is actually a part that's been long abandoned by physics. So this is ordinary string theory in 26 dimensions, which physicists are no longer interested in. You're more interested in superstring theory in 10 dimensions and various other related theories. So what string theory gives you is it gives you a big space V, which is got by taking the group ring, let's work over the complex numbers, the group ring of this lattice and tensing it with a polynomial algebra in enormous numbers of variables, alpha n, for alpha in the corresponding real vector space or complex vector space, and n a positive integer. So here we have a polynomial algebra in 24 times infinity variables. So we've got this really huge vector space. And string theory gives you vertex operators, which are formal power series mapping V to formal power series, or rather Laurent series, with coefficients in V. And you get such an operator for U in the lattice 25, 1. So these were the original vertex operators, which you write by exponentiating something complicated and normal ordering it and so on. And we also get vertex operators from polynomials in the alpha n's. So these give you another vertex operator. And I was studying Frankl's work trying to understand these vertex operators, and it doesn't take long to notice that if you've got a vertex operator for everything in here and a vertex operator for everything in here, then maybe you should combine these and have a vertex operator for any element of V. So every element of V gives you a vertex operator, which is a map from V to V to Laurent series in V. In other words, you're getting a sort of algebraic structure. So we've got a bilinear map from V and V to, not to V, but to Laurent series in V. So this is sort of the beginning of an example of a vertex algebra. Well, if we've got a bilinear map, we should ask, what identities are there? And what we have is, for each element of V, we have some power series. And you can ask, are these formal power series commutative? And we can ask, is this true? And there are two answers to this. One answer is no, and the other answer is yes. If you just write these out as, expand these as formal power series in x and y, then the coefficients aren't the same. However, if you multiply both sides by a power of x minus y, then, at least if you apply them to w, then vyux w times x minus y to the n, if you multiply these both by power of x, the same power of x minus y, they become equal. So what on earth is going on here? Well, let me give a simple example of this. If you take the power series 1 plus x squared plus x cubed, and so on, and compare it with minus 1 over x, minus 1 over x squared, minus 1 over x cubed, you might say these are quite different. The coefficients are obviously not the same. However, if you multiply this by 1 minus x, it just becomes 1. And if you multiply this by 1 minus x, it becomes 1. So these different formal power series become the same if you multiply them by 1 minus x. So something similar but more complicated is going on here. Now, once you've discovered this, it's quite easy to write down some identities satisfied by the coefficients of these operators. For example, you see that ux vy in some sense has poles at x equals 0, y equals 0, and x equals y. Now, if you think about the variable x, if you look at the x-plane, there are poles at 0 and y. And now, if we integrate in a big contour like that, it's the same as integrating, doing a complex integrate around y and around 0. So this gives you, if you carry out this integration, this gives you some sort of identity saying something is equal to something else plus something else. And this is more or less gives you this identity here that I wrote down here. Actually, it gives you a slightly more general version of this identity, which kind of also incorporates this identity here. So that's how the identity for vertex algebras could have been discovered. In fact, this is not how the identity for vertex algebras was discovered. What I actually did was I had no idea what was going on, so I spent several weeks and months writing out hundreds of pages of messy identities involving the coefficients of these vertex algebras and just fiddling around with them, and by a very long-winded roundabout process found the identities they satisfied. I could have saved an awful lot of time if I'd understood what was going on and just directly used this calculation here. So in particular, one of the vertex algebras identities or operations is u0 of v. You remember there's an operation un of v for every n. And u0 of v satisfies the Jacobi identity, or at least one form of it, for Lie algebras. So in other words, if you set uv equals u0v, then we almost get a Lie algebra on v. And we don't quite, because it turns out that u0 of v is not equal to minus v0 of u, which would have to be for a Lie algebra. However, if you take the space v and quotient it out by the image of d and its divided powers, you find this is a Lie algebra. And now, if we take v to be the vertex algebra of this 25-dimensional Lorentzian space that I started with, we find that v over dv contains the Lie algebra of the Leech lattice. In other words, the Lie algebra whose Dinkin diagram is the Leech lattice that I started off with. Furthermore, we find that it contains as a natural subalgebra a Lie algebra whose multiplicities are exactly P24 1 minus R squared over 2. So this is actually a little bit bigger than the Lie algebra associated with the Leech lattice. So Frenkel's observation that the upper bound is equal to this number here is sort of explained because the Lie algebra of the Leech lattice is contained in the slightly larger Lie algebra, whose root multiplicities are given exactly by these numbers. This Lie algebra, incidentally, is the original example of a generalized Kac-Moody algebra. Generalized Kac-Moody algebras were defined specifically to understand this particular Lie algebra with these particular root multiplicities. So I want to just mention a few myths about vertex algebras and try and dispel them. The first myth is that vertex algebras are defined over the complex numbers. Vertex algebras can be defined over the integers, and the theory works perfectly well over the integers. Nearly everybody defines them over the complex numbers, but there's really no good reason for this except that people are nervous. There are plenty of interesting examples over, for example, finite fields. For instance, you can find examples acted on by Chevalier groups. So Chevalier groups are defined over finite fields, and they act on vertex algebras over finite fields. And Alex Rieber noticed that there are various examples over finite fields acted on by sporadic groups. For example, the baby monster acts on a nice vertex algebra over the field with two elements which can't be lifted up to characteristic 0. So you really shouldn't define vertex algebras over the complex numbers. This eliminates a lot of interesting examples. The second myth is that vertex algebras were not motivated. Well, the myth is that vertex algebras are motivated by conformal field theory. In fact, they weren't motivated by conformal field theory because I had no idea what conformal field theory was at the time. They did turn out shortly afterwards to be connected with conformal field theory, but that was noticed by other people, not by me. They weren't really motivated by the monster either, at least as far as I was concerned. Again, shortly afterwards, it turned out they were related to the monster, but the original motivation was not the monster, but the Lie algebra of the Leech lattice. The third myth is that vertex algebras are a sort of analog of Lie algebras, and they're not. Vertex algebras are not a sort of Lie algebra or a generalization of Lie algebra, but are a sort of analog of commutative rings. In fact, any commutative ring is automatically a vertex algebra. We just define A minus 1b to be the product in the rings and all the other things equal to 0. More generally, they're analogues of commutative rings with a derivation, or more precisely, a derivation with divided powers, which you can actually think of as being a commutative ring acted on by a formal group. And this is really the best way to think of vertex algebras. A vertex algebra is sort of like a commutative ring acted on by a formal group, except the ring multiplication is not defined everywhere, but it's sort of a meromorphic function of its arguments. So informally, if we write the group action of a group element x on a ring element A as a to the x, then you can write identities like a to the x times b to the y, and you can think of this as being a function of x and y. And in a regular ring, in an ordinary commutative ring, this would be a regular function of x and y. In a vertex algebra, it's a sort of function of x and y that may have poles. So it's not actually defined for all x and y in the group. In particular, the ring multiplication may not be defined because that may lie at a pole of this. And all sorts of identities which are obvious if you write this as in terms of rings acted on by groups, turn out to be vertex algebra identities. For instance, this is equal to a to the x times b to the y, c to the z. So this identity looks completely trivial if you think of it as being a ring acted on by a group. But in terms of vertex operators, it would look like this. And it turns out to be a non-trivial identity involving vertex operators. So that was the original example of a vertex algebra. It was the vertex algebra of a lattice. So it was quite difficult at first finding further examples. So let me list some of the early examples. So first of all, we have commutative rings with a derivation. So these are the sort of uninteresting examples. Secondly, we have the vertex algebra of a lattice. And perhaps the most famous vertex algebra of all was the one constructed by Frenkel, Lepowski, and Merman. This appears in their book on vertex algebras, which appeared a few years later, and gives the cleaned up version of the definition of vertex algebras. So they reformulated the definition in terms of formal power series rather than writing out all the components explicitly, which makes life a lot easier. So this gives us the monster vertex algebra. And the monster vertex algebra led to the moonshine conjectures, which I'm not going to say much more about. That's another story. And for a long time, I didn't really know of any other examples of vertex algebras and had a hard time getting anybody interested in them. I think there was one time I gave a talk and there seemed to be an awful lot of people in the audience, and I thought finally people are getting interested in vertex algebras, and the answer turned out to be the title of the talk had been misprinted as vortex algebras, and a whole lot of people who thought this was something involving fluid dynamics turned out up to hear what a vortex algebra was and seemed to be a bit disappointed by the talk. But anyway, eventually Frenkel and Zhu found some more examples of vertex algebras. They found that if you take a highest weight representation of an affine Lie algebra, then this quite often has the structure of a vertex algebra, or sometimes it's a module over a vertex algebra. And instead of taking an affine Lie algebra, you can also take the Virasoro algebra. So we finally started getting a reasonably large number of examples of vertex algebras. Frenkel, Lepowski, and Merman's construction of the monster vertex algebra was the original example of something called an orbifold construction. So in terms of vertex algebras, what this means is you take the vertex algebra and take its fixed points under a group action and then maybe add on something else. And it's very hard figuring out what the something else is. It's still rather difficult to construct orbifolds of vertex algebras even today, more than 30 years later. Okay, well, I think that's more or less a summary of the early theory of vertex algebras. Well, so what's the moral of this, as the Duchess would ask? Well, I guess the moral is if you find a really bizarre, weird example, such as Conway's description of the reflection group of the 26-dimensional Lorentzian lattice, it's really a good idea to spend a lot of time poking around with it and seeing what turns up. So general theories like, say, generalized Kac-Moody algebras or vertex algebras don't usually arise because someone was trying to invent a general theory. They arise because, very often, because someone was looking at one particular interesting example and trying to understand this. So if you find anything bizarre going on, you should really try and focus on it.